Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. My name is Karen Strauss and I'm in the Computer Architecture group, and today it's my pleasure to introduce Adrian Sampson. Adrian is a PhD student at University of Washington. He's currently working with Louis Sezzi, who's here in the audience today, and Dan Grossman. And Adrian is no stranger to MSR. He's actually done 2 internships before, one with me and one with Catherine McKinley. And today he's going to talk about programming approximate systems. Adrian.
Thanks so much, Karen. Hi, everybody. So I'm going to talk today about approximate computing, which is what I do as a PhD student. Can everyone hear me? Okay, is this cool? Good. All right. So I have I'm going to do a little bit of background on what approximate computing is, if you've never heard of it, and the sort of programming language aspect, which I think is one of the organizing forces behind how approximate computing should work in the future. And I'm going to do a sort of high-level overview of a couple of the component projects that we work on, because there's like many different ways you can think about approximate computing. I'm just going to talk about 2 to keep it short. And this is a pretty high-level talk. I've only gotten at the sort of the most interesting 5% of the idea. But if you but that means that I would like you guys to slow me down if there's any technical stuff you want me to talk about in more detail. So just interrupt me if it ever seems like I'm glossing over the important things. Does that sound good? Cool, great. And so about approximate computing, the idea behind approximate computing is that lots of the applications the most important applications that we can think of today have something in common. If you think about applications like robotics, or things like large-scale physical simulation, or some of the most important applications of all, mobile gaming, the common thread among them is that there's not a hard and fast notion of what correct means. Is that there's a certain tolerance to a little bit of variation in how the program behaves. If a few small things change in your climate simulation, for example, that doesn't fully compromise the overall usefulness. You can imagine a few bit flips or a few rounding errors not being catastrophic when you're talking about a sprite in a video game being a little bit off. That the game is still useful and it might even still be playable if the computer is allowed to be a little bit wrong when it does the computation involved with the game. And it's not just these applications. You can keep on thinking of more and more programs that have this property of error resilience at the application level. And if you're like me and you've been thinking about approximate computing for a while, like once you have a hammer, the entire world of applications start looking like nails, and that you can start to see this error resilience present in lots of the applications that you care about. And the idea behind introducing errors intentionally into the way the computers behave has obvious problems, right? So you might imagine, for example, an image renderer that when you inject errors into it does something like this. In particular, what I mean is that in the upper left we have an output of a very simple ray tracer, and it's completely correct. I just ran the program on a precise computer. And then the other images show varying levels of error injection. So during the execution of this program, I flipped some bits during some arithmetic operations and during some storage. And in the lower right, you see a pretty bad output from that. But in between, there's some outputs that look okay. And the goal, of course, is that we want to choose something that has not that many errors, but can save us a lot of energy. And what I mean is that what if we could design a computer that, when it's allowed to be wrong, can be way more efficient than a computer that we force to be completely correct all of the time, blind to the fact that the application can actually tolerate that. So we'd like to select an output that makes a good trade-off. But in reality, you're probably wondering to yourself, like, why does a bit flip only affect a few pixels in the output? And in general, that's not true. You can imagine that sometimes when errors occur randomly distributed through a program, there's no graceful degradation from completely precise to not very good. It looks, the outputs don't look like that slide a while back. They would look something more like this. That is that bit flips in certain parts of a program can cause catastrophic failures. That is that even one single bit flip in a pointer, for example, might cause the entire program to go completely wrong. Which is why approximate computing is challenging, is that we want to find a good trade-off without compromising the essential reliability of the program. And that motivates a lot of the work that we do in approximate computing, trying to make it feasible for people to reason about how errors can impact a program to exploit these quality and efficiency trade-offs that we think are present at the hardware and software levels without completely compromising the way that application works. So the work that we've been doing at the University of Washington, and some other people at other universities have started to look at, has really had to address this from a whole stack perspective. It doesn't make sense just to think about hardware, for example, and just to say, what are some ways I can make hardware more efficient while allowing a few errors? It doesn't work that way. We need to incorporate properties of the applications and the way the programming languages work and the way that compilers interact with the hardware to make good trade-offs. And that's what I'm going to talk about today, is a few points along this system stack. And some of the things we've worked on in the past have been a programming language called Energy that lets people express approximate programs and to enforce the safety properties that try to address the catastrophic failure question that I brought up before. And we're also interested in ways that compilers and hardware can get involved. But in particular today, I'm going to talk about a little bit about background on Energy, which is the programming language that sort of ties this all together, and then a little bit more on more recent work on storage, approximation for storage in phase change memory, which is about to be presented next week at Micro. And after that, I'm going to talk about a compiler-based approach to all software approximation, which is unpublished and super new work. So this is the outline for what I'm going to talk about. I'm going to talk about just a little bit of background on Energy, and then some hardware stuff, and then some software stuff. Anyone have any questions at this point? And I left the gray things on the side, just in case you're interested in talking later about CPUs, doing approximation in CPUs or in accelerators. We have an interesting idea for using neural networks as accelerators for approximate programs. Cool, great, thanks. So let's talk a little bit about the programming language perspective. And the reason that I'm bringing this up now, even though it's about 3 years old now, we published this in PLDI 2011, is that it really it captures. I think a programming language is really necessary for letting programmers express approximate programs. Currently, when you write a program, there's no notion of error resilience in the way that you write the program, and we need a way to get around this problem. That is to say, we want to relax programs. We want to allow incorrectness without allowing this type of incorrectness. So we don't want to allow crashes or arbitrarily bad behavior. We would like to guide the program to a sort of continuous trade-off space between accuracy and efficiency. And the way we do this is to ask the programmer to divide the program into the error resilient and the critical parts of a program. As you can imagine, things like jump targets and pointers on the one hand being needing to be completely precise, and we'd like to isolate those from sort of the bulk of the data that the program is working on. For example, the pixel values in that ray tracer example that I showed you, or the frames in an image renderer. And the idea is we would like to keep the precise part of the program precise while allowing the bread and butter of the program, the actual data that's being computed on, to be relaxed. And
would you allow us to say that the least significant bits are less important than the most significant bits of pixel data, say?
That's an interesting point. This distinction is all about what needs to be completely precise versus what can be approximated at all. Right? So that's what your question about whether about certain bits being more important than other bits is sort of a question of degrees, right? So once we decided something can be a little bit approximate, there's a question of how much can it be approximate. I'm actually not going to address that in this project, but there's a few other. Let's talk a little bit later about how you might control that. But that's a very good point, right? Is that right now what I'm talking about is finding is this sort of first cut, which I think is the first sort of design decision, which is where can errors be allowed at all, even a little bit, where even a little bit of errors can cause precise things to go very wrong. And then the rest, we need some sort of tuning system or something to decide how approximate that could possibly be. And what I think that a programming language can help programmers do in this situation, once we've asked the programmer to make this distinction between critical and non-critical parts of a program, is to help isolate those. That is, we want to prevent the programmer from accidentally shooting themselves in the foot and taking taking data from the Wild West of the approximate part of the program and letting it flow into the precise part of the program, causing arbitrarily bad behavior. The second thing that a programming language can help do is to provide some degree of generality. Lots of people have lots of ideas about how to do approximate computing, about how to make efficiency-accuracy trade-offs. But it'd be great if we had a single construct, something unifying in the language that let programmers just express approximateness in the abstract. And then the runtime can map that down to any type of approximation that you can imagine. For example, we've been interested in ways that you can approximate the logic in CPUs, maybe by using a lower voltage and allowing timing errors to happen sometimes. I'm going to talk later about storing data approximately, allowing a few bit flips when you read data back after storing it, and also about even about approximate algorithms, so nothing involving the hardware at all, but a different algorithm that is less accurate than the completely precise computation. So that's what NRJ tries to provide, is a notion of safety, that is protecting critical data while allowing approximation in the bulk of a program's data, and generality, that is using some sort of single language construct to map, to express approximation in the abstract. That makes sense as a motivation for an approximate programming language? Cool. The answer to how we accomplish that is actually very straightforward. The idea is to add type qualifiers to the language that mark data elements as either approximate or precise. So here is a tiny bit of pseudo-Java where we have two variables, and you can just mark any type in your programming language as either approximate or precise. And the isolation property, the flow invariant that we want to allow precise data to flow into approximate data, but not the other way around, is just enforced using the type system. So if we can make our subtypes work correctly so that you can assign precise data into approximate variables, but not the other way around. This prevents you from taking potentially corrupt data and letting it flow into data that you marked as precise. To make this a little bit easier, we make the precise qualifier implicit, meaning that you can take a normal Java program and compile it as an NRJ program, and that is a completely precise NRJ program with the same semantics as the Java program. But if you can incrementally add these approximate qualifiers to selectively allow approximation where you think it might be possible. And the way this usually works is you look at a program and you find that bulk of the data, that pixel array or something, and you mark it as approximate, and you follow the type errors that the compiler gives you to mark all the things associated with pixels as approximate.
Am I allowed to say if A is bigger than 0 in this program, then do this? That is to say, is the program counter implicitly precise?
It is, yeah. So the answer to your first question is no. Right.
It would always be thrown out if I said if A is bigger than 0.
Right. Yeah. So right. So what that means from the language there is that conditionals have to be precise in our language. That's the way we get around implicit flows. You can imagine more complicated things, but this actually tends to work okay. Yeah.
Do you supply sort of a switch or whatever, some sort of simultaneous switch over thresholds on A? So it's fine providing you say some of the A's go to the left and some go to the right.
That's a really interesting point, right? Where if your control flow is if you can show that control flow only affects approximate data, then you can imagine a more sophisticated way of reasoning about how conditionals could influence the other approximate programs. But for the moment, we don't even do that, right? Like, I guess the simplest example is you have if approximate condition assigned to approximate value, right? That's probably fine because how
else would you express thresholding, for example?
Right. Yeah. That totally makes sense. Yeah. And at the moment we don't do that. The solution is obvious, but for now we found that it was fine to just say, please don't do approximate conditions. But of course, there's a way to get around that, which is we provide an escape hatch to let programs explicitly mark the points where this flow invariant can be violated. We put endorsements into the language, which acts just as a typecast to say this value of approximate type is allowed at this one point to flow into approximate values. This lets the programmer sort of isolate the points where things need to be checked to make sure that they make sense as they flow from the approximate part of the program into the precise part of the program. This example on the slide is one pattern that we see a lot, which is to say you do something expensive, and then after that you want to do some sort of cheap checksum. When approximating that checksum would be bad for two reasons. First of all, it doesn't buy you much because the checksum is cheap, and second of all, you probably want that checksum to be correct. Even if the input data is approximate. So at that point, you want to endorse the value to make sure that it is allowed to flow. So we provide this endorsement construct, which just explicitly lets the programmer say, this is fine, I know what I'm doing. That makes sense? That's a really high-level overview of the programming language NRJ that sort of ties the other two projects I'm going to be talking about today together. But I've left out a lot of details about how the language works, so if you have any questions, now is the time.
Are you going to get into examples of the output or something like that we can see?
I don't actually have example output slides here, except for the example you saw earlier in the program, that ray tracer was a real NRJ program running on simulated approximate hardware, showing you the examples with crashes, those were made up, but the ones with the graceful degradation, that's a real NRJ program that we annotated to allow that trade-off.
And there's just like a slider for what's degradation you want?
Right, yeah, and in this case that was running on a simulated hardware with a number of different approximation techniques, and each of them have a parameter. The question of parameter selection, that is where in the trade-off space you want, is an interesting one, and we'll actually get to that in the third section of this talk. Cool. Great. So the next project I want to talk about is something we're working on lately and this is more from a hardware perspective, which is the idea of approximate storage. Is that there have been lots of projects about doing computation that is to say take your functional unit and you run it at a lower voltage. Sometimes it can be wrong, but now we're interested in ways that you can exploit storage technologies to store data in a way that that is not guaranteed to return exactly the bits that you wrote. And we'd like to sort of exploit some properties of the underlying storage mechanism in order to make that the most efficient and to mitigate errors even in approximate data. So what I'm going to be talking about in this section is phase change memory. And as a quick review, if you haven't heard of PCM, we like PCM. We as the architecture community like PCM because it probably offers the ability to scale beyond DRAM's limits. And what I mean by that is that people are worried now that DRAM is on the verge of not being able to scale any further. So we need some new memory technology to come along and save us as we try to continue scaling memories. And it has these nice benefits on the side, which are that it is quite a bit faster than Flash, and it's almost as fast as DRAM, that it might make a good main memory replacement. And on top of that, it's non-volatile. So it can be used both for persistent mass storage, like Flash or hard disks are used today, and for main memory, like DRAM is used today. But it has some drawbacks, and that's what a lot of people interested in PCM have tried to address. The two drawbacks that I'm going to talk about today have to do with multi-level cells, which allow you to increase the density of storage in PCM, but at a trade-off in the access latency. That is, it's a lot slower to write to and read from multi-level cells, a multi-level PCM, than it is single-level PCM. And it also has this a troubling aspect where things wear out relatively quickly, compared to DRAM, meaning that individual bits and cells in your storage system can fail and become stuck at a certain value relatively early in the device's lifetime. And both of these have to be addressed if we're going to make PCM reasonable for main memory storage or even to replace Flash. Because I'm an approximation person, and again, I have a hammer and everything looks like a nail, when I see these two limitations, I implicitly add something to the end of each of them, which is that multi-level cells are slow if you want to store exactly the right value. And cells can wear out, and you have to throw away blocks of data if you want to actually store the correct data in those cells. On the other hand, if you're willing to compromise on that, if you're willing to store slightly wrong data, then you can help address both of these quirks of PCM. As you might be able to make multi-level cells faster, and you might be able to use more of your memory for longer if you're willing to tolerate a few errors during them. So the two techniques I'm going to talk about right now are, one, trying to trade off accuracy for access efficiency in multi-level cells, and two, ways to use blocks that have dead cells to store precise data, to store approximate data. So the first one I'm going to talk about is this multi-level cell idea. So as background, let's look at how a single-level cell and a multi-level cell in PCM work. So PCM, like lots of other solid-state memory technologies, a cell is just you can think of as an analog storage device, and we're just quantizing it to a digital value to make it make sense for the rest of the system. And in a single-level cell, that there are only two levels. That's a little bit of a misnomer. There's actually two levels in a single-level cell, but there's a zero level that is a low analog value. In PCM, that's a low resistance set in the cell, and then a high resistance, that's a 1, and the right mechanism is relatively obvious. You can either increase or decrease the resistance to get a 0 or 1 stored in the cell. And a multi-level cell, as you might expect, has lots of different levels. Here's a 2-bit multi-level cell or a 4-level cell that can store, that has 4 different analog values that correspond to digital values for the rest of the system. And because although we're using a digital abstraction to use these multi-level cells, underlying that digital abstraction is still an analog storage medium. And we're conveniently able to ignore it because the people who have made this multi-level cell have tuned that so that you can completely ignore the fact that analog style errors are possible. They're just so rare that you never see them once the value is abstracted into the digital domain. So you can think of it a little bit like this. So say you want to write a 1-0 to this cell. The analog value isn't going to be some precise analog resistance stored in the material. There's going to be a probability distribution because the write mechanism and the read mechanisms are probabilistic. They're not reliable like you might expect in the digital domain. Like in the analog domain, things can go wrong. And the idea behind approximate storage in these multi-level cells is just to allow those probability distributions to be a little bit wider. And and hopefully we can find a way to make it so when you're writing a multi-level cell or reading a multi-level cell, that when you put less stringent requirements on the width of that probability distribution, you can make the accesses much faster. In particular, the way this works is to exploit the way that people currently build the write and read mechanisms for multi-level cells. So let's talk about writes. The way that this currently works is to use an iterative write process, because each individual step is not accurate enough to, if you want to write a resistance to a multi-level PCM cell, you have to heat up a material and cool it down in such a way that it converges on the correct resistance. And it's not possible to do that in a completely accurate way. You can't just do that on a one shot and hope that you get the right answer every single time. People haven't built something that accurate. So what you use is an iterative process where you use a series of pulses to get closer and closer to the analog value you want to store in the cell. And this provides an opportunity for approximation, which is to say that if you're able to use fewer steps to program your cell, fewer coarser granularity steps, and you allow values to fall farther from the correct analog value, then those writes are faster. Another way of putting that, let's change this graph a little bit to show the actual probability distributions, is that here's some probability densities for how writes might go in a precise cell. That is, these cartoon probability distributions are showing a zero or negligible overlap in the probability distributions when you're trying to write each of these levels to the cell. And what we're trying to do with approximate storage is to say, well, we'll allow things to be slightly more distributed from the correct ideal analog value so that those probability distributions actually overlap in a non-negligible amount. And that means that writes can go quite a bit faster while allowing a little bit of level confusion among those values. And what we found when we evaluated this is we were able to accelerate the writes that was by about 1.7x, meaning that there was a reduction in the number of write steps, meaning that each individual write was about 70% faster than a precise write, over the average of precise and approximate writes in approximate programs.
You can't really say it takes 70% faster unless you say with what probability, you said previously you said negligible, and now it's at some probability you might get it wrong. Mm-hmm. So
yeah, so
70% faster to get a 10% probability of being wrong?
That's actually exactly right, yeah. So what we did is we took a bunch of programs and we simulated them on this type of hardware, and we tuned the knobs for how fast these writes went. And we took the highest error run that had under 10% output error, and we said, and we looked at what the average write speed was for those applications. And so this actually brings up an interesting question, which is, what do I mean by output error? Right,
the device itself,
no, actually for the program.
That's very different.
What's that?
That's completely different.
It is completely different, yeah.
Because the program might hide a lot of errors. Do you know what the answer for the device itself would be?
Yeah, so we have that too. I don't have the number right now, but the bit error rates are like on the order, depending on the program, depending on how approximate this is allowed to be, the resilience of the program. It's something between 1% and like 10 to the -9 probability of bit errors.
Which essentially says that the program is amplifying the errors. The program output could amplify the errors at a cell level.
Oh, of course you could. Yeah.
Right, yes.
Amplify arbitrary.
Right, exactly.
Like blue
right,
screening
yeah.
on you. Yes,
so,
but
that's why we show both. So both the device hardware as well as what will happen in the very output of the program, right? So
right, yeah.
But bit errors aren't a good measure here, right? Because
right.
You should really report somehow the scalar deviations.
That's a really good point. Yeah, so what you're bringing up here is that in this particular error model, unlike a lot of other sort of just raw bit flip error models, that it's like nearby levels are more likely than far away levels. And that actually brings up an interesting coding theory question that we haven't solved yet, which is to say, if you, here we have a 4-level cell, and you can only store 2 bits in it, but 2-bit numbers aren't all that useful. And the error model is great because like a 1-value error when you're storing 2-bit numbers is relatively likely, but a 3-value error is relatively unlikely. But what if you want to store anything larger than a 2-bit number? How do you combine multiple approximate cells to get the ideal error distribution? And we don't have an answer to that. It's an interesting question.
It's a gray code, isn't it?
A gray code is actually not exactly what you want. We thought about this too, right? But a gray code means that like if a multi-level gray code is what you would have to use, right? Which would mean that and that means that only one. Okay, so you have 4 multi-level cells representing an 8-bit number, and each cell has 2 bits in it, right? Then an increase in 1 means that any one of those cells can change by 1, right? What I mean to say is that if say any one of those cells has a 1-level error, then that could map to a high bit failure in the represented number. And when you simulate this, it doesn't turn out to be any better. In fact, it turns out to be a little bit worse than the naive take your bits and divide them up by the number of cells. So again, we don't have a perfect answer. What we do, which is a little bit better than the naive thing, is to sort of interleave the bits. So again, let's say 4 levels. Then one of the cells. So you map the highest order bits of the number to the highest order bits of all of the cells. So you have an 8-bit number, and you take the 4 highest bits of the number and distribute them among the high bit of each of the 4 cells. You take the 4 lower bits and distribute them among the 4 lower bits of the cells. But that seems to do a little bit better. But that's...
So if you just aligned all your floats, could you make sure that the sort of least significant bytes were stored in PCMs where you were using a lot of a lot of levels, and the higher order bits were stored in PCMs where you used a few levels.
Totally, yeah. We didn't evaluate that. That would be really nice, though. Yeah, totally. If you had the granularity where you could take the exponent, say, and put that in precise storage or something, and you take the mantissa and put that in this type of storage, that would be great.
Can you mix SLC and MLC in a sort of fine grain like this with PCM?
There has been research on this. We didn't evaluate this particularly, but people have done this for the precise domain, which is to say that if you're willing to spend all the extra time for MLC over SLC, then you try to make this a parameter, right, and make the level count a parameter, and it is possible. No one has actually built this yet, so who knows whether it's actually feasible, but it is possible. Yeah.
You may be able, I think with hardware today, you may be able to do it at the line granularity, but within a line, I think you still have to use nuancing.
I think there's if you think about ways to store an image, right, there's an old-fashioned way where you start at the top left and sort of lay down bits into memory, and each one is either a high significant bit or a low, right? And then there's a slightly less old-fashioned way, which is a JPEG way, which you could think of as dot plotting the whole image with a bunch of basis functions, right, of various cosininess, right? Some are high frequency, some are low frequency.
Yeah.
What was that?
Various cosininess. But then there's the compressed sensing way, where you dot product the image with just random vectors, right? And the great thing about the bits you get from the random vectors is that they're all the same.
Yeah.
If you lose any one, it doesn't really matter, right? The accuracy is the number of bits you got. So if you just had a bit flip memory, that would seem like the obvious mating, compressed sensing, bit flip memory. I think it is interesting to talk about these analog ones and find a sort of a compressed sensing into 2-bit quantities. So you'd have pairs of random vectors with good properties. So I don't know if that's...
That is a really good point. Yeah, is that the JPEG way seems not right.
It's the same as the high order bit way.
Yeah, right.
Exactly.
Cool. So that's that technique for multi-level cells. So I'm going to move on now to talk about cell failures, which is the other big bugaboo in using these future memory technologies like PCM. And that is that we need to be able to, because errors can happen like within days of turning on a PCM array. It needs to be possible to tolerate errors in PCM. And this is true also of Flash. So if you're familiar with Flash, then you can think of this as an analog. Whereas as in PCM, the thing that melts the material, the chalcogenide inside of each cell, that can break, and you're no longer able to store. You're stuck with the value that is currently stored in the cell. And this is, if you're thinking of Flash, then you can think of charge accumulating in the cell, and you can no longer effectively change that without it reverting to a zero very quickly. So what that means is you can think of a block of PCM data, a block of Flash data, as having unusable cells in it. And each block in your memory has some number, at any point in time, has some number of cells that you can no longer use to store data reliably. And how one normally deals with this is to append to each block some amount of error correction. This is in the abstract, but you append some amount of extra bits to each block in your memory to say, I can indicate the bits and I can correct the bits in the main part of the block that are failed. And what this usually means is that you have a finite amount of correction resources. And you can't use the entire memory for correction, so at some point, each block exceeds its correction budget. And by that I mean that the error correction is allocated to correct, in this example, 2 bits that are failed. But eventually you're going to have 3 bits failed. And at that point, all you can do is throw away the block. And so the capacity of a device decreases over time, and eventually it becomes so small that you have to throw away the PCM array. And this is the way that Flash works too. Of course, when I see something like this, I say this is not necessarily a dead block. This is just an approximate block. We'd like to take blocks like this, and instead of throwing them away entirely, let's try to use them to store the program's approximate data. So we learned that programs need both precise and approximate storage, and they have a relatively large amount of data that can have wrong values. So let's take that and put it into the blocks that have uncorrectable failures and see what happens.
Another alternative would be to increase its correction budget. So then the data density goes down, but that's unsurprising because there are lots of errors.
Yeah, so that would be the traditional way to deal with this. But eventually...
So they don't turn it into a dead block, they just turn it into a less dense
Oh,
block.
I see what you're saying. Yes, right. It is to some sort of way of flexibly increase the amount of error correction when errors become more prevalent. That becomes more and more expensive. So what I've actually drawn here is not too much of a cartoon. Like the efficient way to deal with this is to actually co-locate the error correction with the block, meaning that there is a finite amount, and you can't go elsewhere to find more error correction. There is research, of course, to make this more flexible, that is to use more resources elsewhere. But you do run into limits. That is, if you had to, like if you stored a pointer, for example, to the location of the error correction for the values, that would quickly get slow, and it would also open you up to errors in the pointer.
Sorry, I just meant you could still co-locate it. You could just move the boundary between the purple and the white.
But then you lose. Oh, I see.
So it
But
would become less dense.
right. But you also lose alignment properties, right? So when we're talking about real hardware, then what you really want is each block to stay, for example, 512 bits. You don't want to. It would lead to efficiency problems if each block could be a slightly different size in memory. You can imagine how that would get hairy quickly. Cool. So what error correction does for you and is to take the lifetime of a device and extend it. So I'm showing the capacity. The blocks that are usable in a PCM array over time. So you can think of the x-axis as the number of writes that have happened overall to the array, and the y-axis as the number of blocks that are still usable. And if you don't have any error correction at all, then the first error anywhere, the first failure in any cell in your entire array means that you no longer have a completely usable system. But with error correction, you're able to extend the lifetime of the array to a certain point, right? So let's say you have a 10% budget. You allocate 10% of your blocks to be hidden from the user, and say like you have a 1 terabyte memory, but we're going to add on a 100 gigabyte of budget of reserved blocks that we're going to correct. That means that you no longer have the advertised capacity once you reach some amount of uncorrectable failures. On the other hand, all that approximate storage is doing for you is to say instead of the y-axis being the number of blocks that are alive, that's the number of blocks that are precise. And we can keep using the array until one of two things happen. First of all, you can run out of precise blocks necessary to store all the precise data in your program. So we want to guarantee to the programming language layer that some of the data never has any errors ever. And so if you don't have enough blocks to store all the precise data, then the usefulness of the memory is over. The other thing that can happen is that errors become so frequent, even in the approximate data, that the quality is so bad, it's like the lower right image of the ray tracer that I showed you a while back, and it's no longer useful for doing computation. But in any case, we get to extend the lifetime of the PCM array. And there's one other trick that you can play when you're doing this, beyond the obvious. Let's use these compromised blocks for approximate storage, which is to say that you don't have to correct the same failures that a precise storage would correct. And what I mean by that is that say you have a block that has 2 failed bits and you have error correction for 2 bits in your block. So we've successfully corrected those. And then along comes another failure, and it's in, say, the high order bit in one of the higher order bits in your block. That's bad, say, if you're storing some values where these bits over here are more important than those bits. And the naive thing to do would just be to say, too bad, you got a failure in a bad place, so we can't really help you with that. But we can do a little bit better than that, which is to say we'll prioritize the error correction. As once we see a new failure, we won't just keep correcting the same failures we had corrected before, but we'll actually correct different bits. And we'll say we'll prioritize the error correction of those bits that can be the most harmful. And this lets us extend the usefulness of the array a little bit longer in that second failure condition. That is to say that when the quality of the storage is degrading too much, we can make it degrade a little bit slower.
How do you differentiate between soft and hard failures then?
In this case, we're only interested in hard failures because those are the dominant source of failures in PCM.
But you said the first time you saw a failure, you then react, so you just assume everything's a hard failure.
Yes, that's right. Yeah, so that's actually the normal failure mode for PCM, by which I mean that the first time I see a failure means that will be failed from here on out. In PCM that holds true, that you don't see a lot of soft failures. Does that make sense?
Yeah, I'm just surprised you don't see a lot of soft failures, because in main memory it's 10 to 1, 50 to 1, soft failures to hard.
Right, in DRAM the error rate is a lot higher, but because this is a system where you're actually crystallizing material, cosmic rays, for example, don't have as much of an effect as they do in DRAM.
Implies the hard error rate is phenomenally higher than.
That's right. Yeah. Right. So that's approximate storage in failed PCM blocks. And what we see here is we're able to extend the useful lifetime of PCM arrays when running a sort of average workload of many different approximate applications by about 25%. So that's all about approximate storage, and I'm going to move on now to the sort of software-oriented, compiler-based approach to approximation. That's unpublished work. So if anyone has any questions about this storage business, now is the time for them.
The complexity of the error correction circuit, it's quite simple for a standard 2-bit error correction. It's not like it identifies the 2 bits it's going to save and then writes the code. What's the increase in complexity if I've got 3 bits and I want to choose 2 to save?
That's a really interesting question, and that thing you said in the middle about choosing the bits to correct and correcting them is actually the error correction that we use, that we extend in this work. So unlike a traditional ECC, like a sected type thing, which is great for soft failures, it turns out to be more efficient to directly indicate the failed bits when you're dealing with hard failures. So there's actually, we're using a scheme that Karin worked on called error correcting pointers, where you actually store the address, the very small address of the bits that you want to correct.
The other thing, obviously, you could do with these stuck blocks with many stuck bits is start moving rarely written data to them. So I'm just wondering what are the applications where you have lots of approximate data which is also frequently written, because that would seem to be the match for this.
Sure, yeah.
Right.
So in the programs we looked at, and the approximate programs we deal with in general, the hottest data tends to be approximate. There's pointers and stuff. There's like some metadata that is also hot that is precise. But for the most part, things like pixel values and audio samples and like neuron weights in a neural network, those things are relatively hot and they're read and written relatively frequently. And those can be mapped to approximate hardware. So we actually don't see a huge amount of cold approximate data, if that makes sense.
Okay, so you can map terabytes of frequently written approximate data.
Right.
Okay.
Yeah.
I think the point was that there's lots of frequently read but rarely written data, which might also be suitable for putting in PCM, like DLL binaries, for example.
Sure, that's an interesting point. Yeah. So are you proposing a scheme where you like find the block with exactly the right failures to fit in the data so that you...
No, I'm just suggesting that in terms of reducing wear on the PCM, that you might choose to store in PCM memory things which you expect to be rarely written.
I see. Interesting. Yeah. So I'm imagining a system now that doesn't have an alternative, right? Everything has to go in PCM, but that makes sense. Yeah.
You could also do it. You could start moving the rarely written stuff to the blocks that are running out of their error correction pointers, right? Before they run out entirely.
Yeah, that's a good point.
So I'm just wondering, there's clearly two different kinds of data competing for this slightly broken memory.
I really like that idea. Put your cold data in the almost failed cells. I haven't heard of anyone proposing that exactly. I don't know. Have you, Karin?
Proposed that, but yeah, it does make sense.
That's a cool idea. Great. Is that all the questions about storage? I'm going to move on to talking about a project that we call ACCEPT, which stands for Approximate C Compiler for Energy and Performance Trade-offs, I think, which is a little bit of a contrived acronym, but bear with me here for a second. So the idea is that we want to take a program written in an approximation-aware language. And for a long time, we've been interested in mapping that to special hardware that has special support for approximation. We have this Approximate CPU design, and we have designed approximate accelerators that are really good at running code that can tolerate errors. But what we'd like to do is say, what can we do today? Can we take an approximate application and map it onto an x86 or an ARM processor that's on the market now? And what that means is that we want to take an all-software approach. What can we do to not use special hardware, not use dedicated approximate storage arrays? What's available at compile time to transform a program to be approximate, to make this type of trade-off? There's actually been a lot of proposals about this in the literature. One of the more famous ones is from Martin Renard at MIT called loop perforation. And it's almost exactly what it sounds like. You have a loop in your program. Let's not execute all of the iterations. Let's skip a few of them and see what happens. This sounds really scary, but it turns out that for some programs, for some loops, that's actually okay. Like if you're doing a convergence loop and some of those iterations only get partially executed or something, that actually is okay. And this is understandably very scary. And I think it's scary too, which is why I would like to bring the notion of safety that we looked at in Energy to this type of transformation. Other types of software-based transformations involve equally scary things like removing locks around data. That is, if occasional erases are okay on some of your data in your program, then let's not lock the accesses to those. You can imagine some parts of the program being written with floating point, but they only need fixed point for certain sections of a computation. So all of these transformations, I can see a few people grimacing actually in the audience about how scary some of these can be. So it would be great if we had a mechanism for finding out where these transformations were appropriate, rather than continuing to publish papers that just say, look, when I took this part of this program and took it from float to fixed, it still worked. Even though it violated the semantics, it seems to work okay. We'd like to have some sort of a framework that gives you an assurance of safety while guiding you toward the right trade-off between approximation and efficiency. So the way that we want to do this it starts with a quality metric, which is something I've not talked about a lot, but has actually underlied all of the work that you've seen so far, which is that we would like programmers to provide us with some sort of a notion of the quality of the output of the program. You can think of this sort of like an acceptance test, but instead of saying yes or no, it says it has a continuous answer between 0 and 1. That says it gives you the continuous notion of the quality of the behavior of an application, given, for example, a comparison between the completely precise output and the degraded output. And you can say, like, 10% of the pixels were crazily wrong in this image, or something like this. And so we would like the programmer to provide us with the original application and a quality metric that goes along with it. And to do software approximation means that we need to automatically evaluate whether some candidate transformations, whether some loop perforation or some synchronization elision is helping the program to meet that quality metric. So the high-level idea, of course, is to produce lots and lots of candidates using a heuristically selected subset of all the possible transformations on a program, and to eliminate those that don't meet the quality requirements given by the programmer. So you give us a quality metric, and we'll eliminate we'll try to eliminate those configurations of the program, those transformations that didn't work out, that led to really high error. And the next thing we want to do is like once we've filtered out things that are obviously infeasible, is to plot a bunch of candidates on a sort of performance and output quality trade-off curve. As we will if you have a bunch of candidate applications and we can run them many, many times and try to assess the output error, we want to select the Pareto frontier of program configurations that make an optimal trade-off between accuracy and efficiency. And these are the programs that these are the configurations of the programs that the programmer should consider. We don't want to prescribe a particular level of output as being the best, but we can plot for the programmer this trade-off curve that exists in the program between efficiency and accuracy. And the way that we do this at a compiler level is to analyze the program and to look for sections of code that are relaxable. This requires some sort of a notion of going from the data-centric annotations that you saw in the NRJ section of this talk, which all talk about individual variables and fields and objects that can be approximate, and to move from that to some sort of code-centric notion of what is approximable. And the way this works is how you might expect. We can analyze sections of code, arbitrary sections of code, like, for example, a loop body or a critical section between two locks, to see if it has any precise side effects. And we say that any region of code that has exclusively approximate side effects is relaxable. That is, we can skip loop iterations, or we can elide the lock around that region. And that lets us move from the data-centric domain, which makes a lot of sense when you're talking about hardware approximation, into a code-centric domain, which makes sense when you're skipping loop iterations or removing lock calls. And what we see here is that depending on the program, this type of technique is quite a bit more risky, but has higher payoff than the type of hardware approximations we've seen that you saw in the rest of the talk. Is that for some programs, that this type of software approximation doesn't buy you a lot. We looked at a video encoder, for example. We were able to speed up, even perforating lots and lots of loops throughout the program, and lighting lots of locks throughout the program, only able to speed it up by about 10%. But for other programs where they're very loop-centric and have lots of approximate data, and structured in a way that they affect only approximate data much of the time, we're able to speed up by like an order of magnitude. But again, this is unpublished work. So.
Just a concrete example. I'm having trouble with this loop thing, for example, which is the most concrete example so far. Even if we know it's doing approximate data, we could say, well, we can leave the whole loop out, right? But that would probably be a bit too approximate.
Absolutely.
So what are you going to say? You just every other iteration of the loop? I mean, how would you decide which ones to leave out?
Yeah, so for loop perforation in particular, there's an obvious parameter, which is how many of the iterations are you going to execute, right? So you say you have an image filter, right? And so it runs on every pixel, and it transforms it a little bit by looking at the neighborhood pixels. One of the applications we examined actually did that. And if you transform only some of the pixels, or if you're taking an average, say you take an average of only some of the pixels, then that's okay. But it's a sort of application-dependent tuning question, how many of those iterations you want to skip. This is sort of the same question you asked a while back about the hardware parameters.
Even if you say, okay, for this loop I'm going to skip some, how do you decide which to skip? I mean, that sounds like you might need to do more work to say, oh, I'm on the 17th one, so I'll skip this one.
Right, yeah.
Can I answer that?
Oh, yeah, sure.
On this machine, there are at least 3 loops, which say if rand greater than 0.99, loop body.
Uh-huh.
Right? One of them is in a nonlinear optimizer, so accumulating part of a matrix product, and it just drops 99% of the accumulations. Because it runs much faster that way, and it doesn't really matter.
So is that what you're doing? You're throwing random numbers in your examples?
Yeah, exactly. Yeah, right.
Oh, okay. So you randomly choose a proportion of the loops to drop.
Yeah. In the evaluation, it was actually deterministic in that the randomness is generated ahead of time, but just to make it cheaper. But but yes, if you just there's not a lot of work involved in trying to skip this, and in the deterministic case, we just do it with bit masks, right? And it's by saying you just have a counter, your loop counter, if it's a for loop, or we add you in a new counter that says if this is the, every time the counter reaches 4, then we skip an iteration and reset the counter to 0, this type of thing.
Isn't this just an expensive way of correcting code? Because the answer would, if somebody's doing 1,000 loops and they should only need to do 500 loops, then the answer should be to just tell them, just do 500 loops.
Yeah, absolutely. Yeah. So one of the aspects of this is it is sort of an interactive process with the programmer, which is to say that we're discovering these aspects of programs, and it may be the most efficient thing to do is that the programmer should go back and reconsider some decisions. The idea here was to make this. What's that?
Which then just says everything is. By this way, you just end up with a precise program.
Yeah, so if the programmer like sees what we're doing and the system except comes back and says this loop should only execute 500 iterations, and the programmer can say, I mean, right now that's applied automatically, and you're right, it's at an efficiency cost. But if the programmer wants to come back and say, I'll do that manually, I myself will go in and execute only 500 of the iterations, and that's fine too. And yes, that becomes precise.
But if the programmer does it, then that's the intent of the programmer. So basically, as if the programmer says, no, I want to keep 1,000, then you shouldn't drop it to 100, to 500.
But no, it's the opposite, right? I actually have code with random execution of the loop body. If you're saying you've got some hardware that can make that code run much faster, save me doing the rand or something, whatever it is, or you can somehow do, I've already annotated the code, right? You can look for if rand then body, and now you're just going to propose different ways of doing it approximately. That seems good. It's like
no, the customer. But you've defined your intent in your code.
Yeah, that's fine.
That's fine.
I've never written if rand do something.
I can truly believe that.
You don't have children, but you do actually.
Well, you could have had, right? So you could have, let's say, if you had some assurance that doing that would be fine for your output, and so you had a way of declaring how whether the output is good or not, then you can have that done for you automatically, so you don't feel unsafe.
no, you've just added a range of options. I can now try this, run approximately this loop body.
And this range of options are these candidates that he tries out automatically. As long as you honor the output quality, you can apply the optimization.
I suspect it's because I don't compute with random with approximate data. But I mean, if you posited the story to me slightly differently, if you said to me we have a method for saying to the programmer, this piece of your program consumes 50% of the power cost, but only contributes 3% to the quality. Would you like to reconsider whether it ought to be there or not? Then I can kind of believe that. But if you say to me, well, I'm just going to randomly throw bits of the program away, I can't imagine, the director of test ever signing off on shipping such a thing, right? Because it's the case of the unfortunate user. How do I, protect myself from the fact that the person who loses the critical iteration happens to be Vladimir Putin?
I think that's totally right, yeah. And one of the pieces of this system that I didn't show was how this actually interacts with the programmer. And so it's a convenient fiction to say this is going to happen completely automatically. Like we'll just annotate the program, and from there out, this auto-tuner will give you the best possible program. But it's true, you want some feedback, right? Which is the way this actually works is to have there's an annotation step. It sort of is a dialogue between the compiler and the programmer. It says if you have a completely precise program, the compiler will come back and say, here's all the things I would really like to do to your program, but you're preventing me from doing it because you haven't put any annotations yet. Here are the annotations you would have to insert. Here is the data that would be affected if I were to perforate this really juicy loop that I really want to perforate. And so it's sort of in this dialogue that you, the programmer, then get to say, okay, I think this might be a good idea. What is the data that's actually going to affect? You annotate these individual things, and the compiler says, thank you, great. Now look at what this quality is that you got back. And so it's by this process that you can you can think of it as the programmer being guided semi-automatically toward a good solution. I agree that sort of taking your hands off the wheel and just seeing where you go might be terrifying. Great. So that's accept, and it brings me to the conclusion of the talk, which is to say that obviously there's a lot more work to do on approximate computing. The two projects I just showed you are just two facets of what I think is becoming a bigger and more exciting field every month. You can imagine this question of how you do compression for approximate storage is a really interesting one. I'm working now on how to analyze approximate programs to try to guess and semi-statically how approximation at the hardware level is going to affect the quality of the output of a program. And there's other places you can imagine using the approximation hammer to hit various inefficiencies in computers, like, for example, how wireless networking needs to use a lot of error correction to guarantee precise communication, even with communicating things like images that don't need to be completely precise. So that's all for my talk, and if you're interested in more of this, here's my website. It's got a lot of all sorts of papers and some blog posts and stuff about approximation, and then our group's website is sampa.cs.washington.edu, and there's all the information you could possibly want there. Thank you so much for your attention.